Hi again, everyone. We'll continue from the last episode of our cardiac series. So we'll continue here with the phases of cardio action potential. As we've discussed, we'll cover all the four phases in detail and see what happens inside the cardiac cells after an action potential happens. Starting from phase 4, which is also called the resting membrane potential. Phase 4 of the cardio action potential represents the resting membrane potential. This happens when the cell is not being stimulated. In most cardiac cells, around 99% of them, known as contractile cells, phase 4 is shown as a horizontal line in the standard myocyte model, as we could see from the graph. The resting membrane potential, it's primarily determined by the difference in ionic concentrations and conductances across the cell membrane. In the ventricular myocardium, the normal resting membrane potential ranges from approximately minus 85 to minus 95 millivolts. This potential is largely influenced by the selective permeability of the cell membrane to various ions, particularly the potassium ions. The membrane is highly permeable to potassium ions and relatively permeable to other ions, resulting in a higher concentration of the dominance of the potassium equilibrium potential in determining the resting membrane potential. The Goldman-Hodgkin-Katz voltage equation can be used to calculate the membrane potential. It takes into account the contributions of various ions. Several ions pumps and exchange mechanisms, including the sodium-potassium ion exchange pump, the sodium-calcium exchanger current, and the IK1 inwardly rectifying K plus current, maintain this electrical gradient. In the excitatory system of the heart, all cardiac cells possess an unstable phase 4 known as the pacemaker potential. Unlike the steady state seen in contractile cells, phase 4 in excitatory cells, such as those in the sinoatrial node, short for SAN, they display slow depolarization until it reaches a threshold potential. The threshold potential is typically around minus 40 millivolts, or it may be reached when the cell is depolarized by an impulse from another cell. The pacemaker potential is primarily due to increased inward currents of sodium and calcium ions, along with a gradual decrease in outward potassium current. Unlike other cells, sodium channels in cardiac pacemaker cells open when the voltage is more negative, immediately after the end of a previous action potential. Now, what happens with the Purkinje fibers? The Purkinje fibers typically do not depolarize spontaneously. Why? It's because due to being depolarized by impulses from the SAN before reaching the threshold potential. Now, the sinoatrial node cells exhibit faster spontaneous depolarization and establishes a cardiac rhythm hierarchy. Under certain conditions, Purkinje fibers can depolarize spontaneously, leading to atrial or ventricular premature beats. For instance, in athletic heart syndrome, there's a sustained training which slows the sinoatrial node rate. What happens here is that it allows the ventricular cells to reach a threshold potential really quickly. In phase 4, known also as diastolic depolarization, it's associated with heart diastole and controls cardiac chronotropism or heart rate regulation. So while the sinoatrial nodes cells receive input from the autonomic nervous system, they also self-activate and they don't need an external stimulus to fire. So there's kind of an autonomic modulation of sinoatrial node that occurs in phase 4. Now let's go to phase 0. Phase 0 is also called rapid depolarization. So in here, a cell is electrically stimulated, and this happens typically by an adjacent cell. As we've discussed before, an action potential happens following a constant trajectory. So it's a sequence of actions that begins by involving the movement of ions, cations and anions, leading to the generation of the cell's action potential. I want to point out that action potentials are binary signals. So what I mean by binary signals is they either happen or not at all. So it really depends if they reach the threshold value. With phase 0, rapid depolarization, the slope of phase 0, known as this part as dv/dt max, it represents the maximum rate of potential change. So in heart muscle cells, the slope of phase 0 is directly proportional to the net ionic current. This phase is primarily due to the opening of fast sodium channels, which then leads to a rapid influx of sodium ions into the cell, which causes that depolarization. The cell's ability to open fast sodium channels during phase 0 is influenced by the membrane potential. If the membrane potential is near its baseline, all fast sodium channels are closed, and excitation opens them all, causing a large influx of sodium ions. But if the membrane potential is less negative, some fast sodium channels remain inactivated, leading to a lesser response and a lower Vmax. If the resting membrane potential becomes too positive, the cell may not be excitable. Potentially, it delays the conduction through the heart and increasing the risk of arrhythmias. In heart pacemaker cells, phase 0, what's important here is that it relies on the activation of L-type calcium channels instead of fast sodium channels, resulting in slower slope. What happens in phase 1? So phase 1 is the actual action potential. So in phase 1 of the myocyte action potential, it begins with the inactivation of fast sodium channels. As you can see, it starts to decrease. There becomes a slope. And this leads to a small downward deflection, as we can see from the graph. And this is primarily due to the movement of potassium and chloride ions. What happens with the potassium ions? They're carried by the ITO1 current, while chloride ions are carried by the ITO2 current. That's a bit too much into detail. But particularly the ITO1 current contributes to the characteristic notch seen in some ventricular cardiomyocyte action potentials. It suggested that the chloride ions movement during phase 1 is due to the change in membrane potential from K plus efflux, rather than contributing to initial repolarization. In cardiac pacemaker cells, phase 1 results from rapid K plus outflow and closure of L-type calcium channels. In phase 2, in the plateau phase now, in this phase, this is sustained. As you can see, there's a straight horizontal line in phase 2. Here it's sustained by a delicate balance between the inward movement of calcium ions through the calcium channels and an outward movement of potassium ions. And the potassium ions travel through a slow delayed rectifier potassium channels. Now there's some minor roles during phase 2 which are played by the sodium calcium exchanger current and the sodium-potassium pump current. This phase is crucial for sustaining muscle contraction. During the plateau phase, there's a reduction in potassium ion permeability. Now let's go to phase 3, which is the rapid repolarization. In here, the L-type calcium channels close, and slow delayed rectifier potassium channels remain open. This leads to a net outward current and a negative change in membrane potential. As you can see, it goes down. The net outward positive current is equivalent to the loss of positive charge from the cell, which drives the repolarization. What happens to the K plus channels? There's a delayed rectifier K plus channels that close when the membrane potential is restored to about -80 to -85 millivolts, which then allows again for it to phase out. IK1 remains conducting throughout phase 4, contributing to the setting of the resting membrane potential. Lastly, we'll go to the refractory period. So from the beginning of phase 4 until the nearly end of the phase 2, each cell is in an absolute refractory period, during which it's impossible to evoke an overaction potential, followed until phase 4 by a refractory period, during which a stronger than usual stimulus is required. These two refractory periods are caused by changes in the state of sodium and potassium channel molecules. When closing after an action potential, sodium channel enters an inactivated state. So this means that they cannot be open regardless of the membrane potential. What happens here is that it gives rise to the absolute refractory period. Even after enough sodium channels have transitioned back to the resting state, it frequently happens that a fraction of the potassium channels in the cell remains open. Why? To make it difficult, but still possible for depolarization to occur. Hence, it gives rise to a relative refractory period. So we've gone over the 4 phases of a cardio action potential. And next we'll be learning how to carry out an ECG. Thank you for watching.